Testing. Okay. Test. Hello. Come on. Hello. 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 Can you all hear me? Yeah. All right. Right. So we're going to continue on this example over here, which is equation of motion, rotation by a fixed axis. I think I have to start recording. Oh, recording started. Okay. Now, I've put up another 2 more examples on Avenue to Learn. If you could download from Avenue to Learn, that would be fantastic. Okay. Yesterday was a big rush that you are worried how to acquire the mass moment of inertia. So I'm going to do the mass moment of inertia about the entire structure again. Okay, that's where I last left off. So we're going to find the mass moment of inertia. Okay, so we have a slender bar and we have a rod. So I'm going to take the, oh, I did not do that. Did I do that? Oh, yeah, this, I'm going to get these 2 images to help of us visualize. Okay, I know yesterday during this time I was a bit rushed. I should not rush. So on the left is a slender bar. On the right is a sphere. And I will, as I said, the formula sheet will have all this information. Do not memorize any of this, okay? So we are going to take, if we look at a moment, we have taken our moment about point O. Point O is at this location over here. So we need to find IO alpha. Okay, so about point O. So if we were to, I'll get this image down here, just the image. Right? So if we were to find the mass moment of area about point O, on the left-hand side, I would like to consider the slender bar. Okay. And then the formula we're going to use, okay, because down here is our G for our slender bar, right? There's an offset of distance, so we have to use the parallel axis theorem. So we know there's I naught is equal to IG plus by MD squared. Okay. Now, if you were to look into this diagram over here, right? Which formula do you use? Do you use 1/12 ml squared? Do you use 1/3 ml squared? Or IZZ is equal to 0? Now, can I be very sure, or are you very confident that it's not IZZ we are looking at? Yes or no? It's definitely not IZZ, because IZZ is parallel to the axis of the what? Of the rod, the axial axis. So it's either IXX or IYY or IX prime or IY prime. So we are going to select IXX or IYY, does not matter. Are we clear? The formula. So we're going to select IG is equal to IXX or IYY. Right? So they call it IG is because this is where the center of gravity is. Okay, this is where our center of gravity is. But our point of interest is point O. So we need to shift the MDX. Okay, so I naught is equal to 1 over 12. If I'm not wrong, yeah, I will be wrong. The mass, I do apologize, the mass of the slender rod is 10 and the spear is 15. So this is 10. And the length is 0.6 plus the mass is 10. The D, okay, D is the offset, so it's equal to 0.6 divided by 2 relative to the centroid. And this will be squared. So when we compute this, this will be equal to 1 over 12. Oh, there's a square down here. Times 10 times 0.6 squared plus by 10 times by 0.6 divided by 2 squared is equal to 1.2 kilogram meter squared. Or we can, Eugene, seriously? Or we can use what? Ix prime or Iy prime. And this will be equal to 1 over 12 ml squared. Oh, 1 over 3, you are right. Okay, 1 over 3 ml squared. So this is 1/3 multiplied by 10 is 0.6 squared. Okay. So 1 over 10 times 10 times 0.6 squared. Okay, so it's 1.2. Now, this equation, this over here, cannot use for I naught is equal to Ig plus by md squared. Are we clear? Because for this formula to be valid, the mass moment of area has to be at the where? Center of gravity. Are we clear? Okay. So I did show off you before, I think of last week or the week before, you cannot use that value to use for the parallax theorem. Okay. So next question so far, anyone? Okay. Then we are going to look at the spear. Spear is easy stuff. Regardless, IXX, IYY, or IZZ is 2/5 mr squared. But because we have to shift to point O, so this will be equal to 2/5 mr squared plus by md squared. Okay. So this will be equal to 2/5. The mass is 15. The spear radius is what? Can't remember now. 0.1 plus by 15 multiplied by a distance. So if we were to look at a distance, this is 0.1. This is 0.6, so it's 0.7. So from here, we have 2/5 times by 15 times by 0.1 squared plus by 15 times by 0.7 squared is equal to 7.41 kilogram meter squared. Let me do it again, please. 17.41 kilogram squared. Okay, so now we have all the information now. So our I total is equal to 7.41 plus by 1.2 is 8.61 kilogram meter squared. Okay. So From here, all we need to do now is put into this equation over here. Okay, so I'm going to have this equation. Right? So now this will be plus. Okay, so this entire equation plus 8.61 alpha. Okay. When we form this equation, right? When we form this equation, if we were to go back to yesterday, right? When we form this equation, when we form this equation, right? We form it at point O. Can you see that? So at point O over there, we already have included all this effect. Okay, like we have included 98.1 sine 45. We have included 147.15 sine 45 already. Okay, and then from here, we just need to do the calculation. So 50 plus by 98.1 98.1 times by sine 45 times 0.3, 20.81. 147.15 times by sine 45 times 0.7, 72.836. And the whole thing will be equal to 8.61 alpha. So now we just need to determine alpha, which is equal to 50 plus by 20.81 plus by 72, okay, 50 plus by 20.81 plus by 72.836. So it's 143.646. And then we just divide by 8.61. So I get 16.684 radians per second squared. Okay. So once we have this, we can find the objective is to find the forces acting at point O. Okay. So if we were to just recap, we have found our ON. Okay, so our ON is equal to 294.981. Okay, so ON 294.481. Okay, so 294.981. Come on, wake up, Eugene. And next, we need to find our OT. And our OT, we have an expression over here, okay, which we derive by summation about forces in the tangential direction is 173.418. Okay, 173.418. And then we minus 13.5 alpha. Okay, so we have determined alpha. So this is 16.684. 13.5 times 16.684. 173.418 minus y. So it's minus 51.816. So minus, what it means when it's minus means our direction that we assume was wrong, right? But it did not really affect our calculation. So in your free body diagram, what you should do is you should cancel this. Do not erase, okay? Just not that level of cancel. It's too dramatic. Okay, and just put this over here, and this is your OT. Are we clear? Okay. As a professional engineer, do not wipe out. Are we clear? Okay, just cancel, then just put it over there. Okay. Right. So from there, finally, we can calculate the resultant forces acting on point O. So this will be equal to 294.981 squared plus by 51 or minus by squared does not matter. Okay, but let's be good boy. Oof. Squared. Okay. So from here, 294.981 squared plus by minus 51.816 squared. Square root of the whole thing is 299.5. Let's do something further. Assume that point O is under double shear configuration. What does this mean? Anyone? Where the shear stress is equal to P divided by what? 2A. Yes or no? Why is it 2A and not 1A? Oh. Anyone? Why is it 2A and not 1A? Because of double and single? So the area that is affected, how do you mean? Why is it 2? Both sides, you cheeky sort. Okay, let me quickly draw single shear